alliance captures their opponent's tower at the end of the match, their flag is raised and the alliance earns more points. The alliance with the highest score at the end of the match earns the win. Step into your castle, proudly raise your team standard, and face the challenge ahead at this year's FIRST Robotics competition, FIRST Stronghold.
I could use this, couldn't I?
Yep.
You're really close, don't you?
Yeah.
Anyway, so I guess I should introduce the presenters here. For a while there, I thought that we were going to have, at different times, a team from Wea and a team from Konawaina. But as it turns out, we're just Kealakhe this year. So please, you want to start, Courtney?
Of course. Right.
You left it all messed up.
What happened to the other guys?
Wea is not doing first this year, and I'm not sure about Konawaina.
Huh?
Do you guys want to use the pointer that will advance the slides?
Yes, that'd be wonderful.
Yeah, that's great.
You don't need to have somebody. Okay, it's on, you just have to click it.
Thank you. So hi, I'm Courtney.
Not quite yet.
Hi, Courtney.
I am a senior, and this is my third year doing FIRST Robotics. And so this year's competition, Stronghold, is a really exciting new step because of the intricate and interesting field, and because we get to touch other robots this year. And if you were here for this presentation last year, we saw that one of the big problems we had personally was we like to hit people with our robots, and we weren't able to do that last time, so we're looking forward to that this time. So, this is us. We are the Tiki Techs. We do over 22 competitions and have over 25 annual outreach events. And so if you'd like to learn more about us, you can check out our website or come visit us. We're at the Kealakhe High School every Tuesday and Friday. And this is our 5th year?
Yes.
No, 4th year.
5th.
5th? This is our 5th year of doing FIRST Robotics. And so this is a season where we really test our team and we make a difference. And so we'll be at the school until 7 on Tuesdays and 9 on Fridays. And we take a lot of nights and we spend the night and we spend a lot of time working on FIRST Robotics, and it's one of our most challenging competitions. And to get more into the game, I'm going to hand it over to Sarah. Oh, sorry, kickoff is Kyla. Kyla.
Okay, my name is Kyla, and I am a junior at Kealakhe. And I'm just going to be talking about FRC kickoff. So, as you can see in the picture, we have Kealakhe, and we have Konawaina in there too. And what we did was, in the beginning of the day, we watched all of the video clips that were released. And right after that, we spent like 2 solid hours reviewing the games and what all of the rules were. And it's really important that all of us know the rules, especially even though not all of us are going to be building the robot. It's really good to all be on the same page, because at competition we can come up to anyone who's wearing a shirt, and it's really good to know the rules. What was really cool is that same day, what Kealakhe and Konawaina did was we're trying to recreate the stronghold defenses that there are in the, as you've seen in the video, and we'll have Ian talk more about that. So that was really cool.
So,
Is the mic on?
along with games, rules, and quizzes, we also started building our robot and looking a little bit at design priorities and game strategy. And I'm going to pass it over to Sarah so she can She can explain to you a little bit more in depth the game, the defenses, and the rules. I don't think it's working. I'll hold it anywhere.
Is it on?
No.
Hello.
Hey.
Hello. I think
There
it's
you go.
working.
Yes, it
Okay.
is.
Hi, I'm Sarah. I'm a senior at Kealakhe, and this is my second year doing FIRST Robotics. Last year I was primarily on documentation, but this year I have started to build, and it's a lot more exciting to me than writing. As Courtney mentioned, this game is called Stronghold. It's a lot more interactive than it was last year because we actually get to connect with other robots. We get to help each other out, and with the opposing team, we can hit them and we can do anything to them, but not really. But not anything. We have to be humble and have to be cautious. So Stronghold is a game consisting of two different alliances, the Red Alliance and the Blue Alliance, and each alliance has 3 different robot teams on them. The purpose of Stronghold is to breach your opponent's defenses, meaning that you can cross over them. The defenses are actually really unique to this year's game. Last year for Cycle Rush, the purpose was to stack totes, and that's all that your robot could do. This year we have 9 different defenses, and they can be arranged in any different orientation. And like the video said, there are over 10,000 different possible scenarios in which the obstacles can be arranged. One alliance can select 3 different, as you can see, there are 5 spots for possible changing of the defenses, and there's one defense that is constant, that remains constant for the entire match, and that's the low bar. It's about 16 inches off the ground, and its accessibility robot is smaller than 16 inches, and you can just drive underneath it. But the rest of the defenses are very intricate in their design, and they really test your ability to build a robot that can cross over them efficiently and effectively. So you score points by crossing over or breaching your defenses, and you score, I believe during Autonomous, you score 5 points for reaching a defense, and you score 10 points for crossing it. And during Teleop, you score 5 points for crossing it. I think that's what it is. I'm pretty sure.
So you score 2 points for reaching a defense, 5 points for crossing it, 5 points for scoring low goal, 10 points for scoring high goal.
As I mentioned, there are 5 different spots for possible defenses. The audience actually gets to participate in this year's game. They get to select one defense that, I will explain the different defenses in a bit. They can select one defense that they want to see the teams participate in, and that's extremely exciting because the audience has never actively participated in the game before, so it's not just up to the strategy of the teams. The teams have to adjust and adapt to what the audience decides as well. The opposing alliance gets to select one of your obstacles, and your own alliance gets to select 3 of them. This game also has 2 tower goals, one on each end. As you can see, there are 3 different spots on your tower, right there, and right there. And the purpose of those spots is for your robot to drive up onto them near the end of the match. If you do that, you score 5 points for each approach, and then 15 points for scaling the robot, or for scaling the tower, excuse me. On the tower, there are 3 different bars, and they're about 10 feet off the groundish. And if your robot finds a way to hook onto the bar and pull itself up, you score an additional 15 points. And that's insane. Like, we've never had events like that in any of our competitions where we had to actually scale something. It's pretty exciting. The tower has a high goal and a low goal, about 10 feet off the ground and right on the ground, where you can score your boulders or your foam balls, and that is worth 5 points for the high goal and 2 points for the low goal. And the human player, there's always been a human player for these competitions. It's pretty cool because this year the human player gets to bowl their boulders. As you can see, there's a red rectangle up top and a blue rectangle underneath. That's called the secret passage. The human player has to bowl one of their boulders and make it into the neutral zone, which is the zone in the middle, and that's how you get your boulders onto the field. These are the different defenses. There are 8 different defenses shown, but there's also the low bar that has not been shown. I kind of briefly discussed about the different point values, but they are right there. The defenses are split up into 4 different categories. Category A consists of the portcullis and the chevaldredries. The portcullis is a device in which you have to lift the bottom of it. It's if you have any experience with like medieval defenses, they
Some of us do.
or garage doors. It acts like a garage door. The portcullis can be lifted up from underneath, and the robot has to drive underneath it, and that's how you breach the portcullis. The cheval de frise is actually a seesaw arrangement of 4 different planks, and you have to find a way to drive over them so that your wheels can actually touch and you can actually drive over it. Category B consists of a moat and ramparts. A moat is just lifted wood, and you have to find a way to go over the bump and then to go over the second bump. The ramparts are secured seesaws. They're like seesaws but secured, and you have to find a way to drive over them, even though they are different heights for your wheels. Category C consists of the drawbridge and the sallyport. The sallyport is a swinging door in which you can drive through, and the drawbridge acts like a regular drawbridge where you have to pull it down and then drive over it. Category D consists of a rock wall and a rough terrain. A rock wall is similar to the moat in that it is a wall that you have to drive over, and the rough terrain is a system of different heights of blocks, and it's like a rough terrain. You kind of have to find a way to maneuver your robot over it, making sure that your wheels don't actually get stuck in between them, because that is one of the main challenges that defense poses. The low bar, as I mentioned previously, is a 16-inch tall bar that you have to, and that's the constant obstacle. Like, if you can find a way to master the low bar, then you can essentially score as many points as you can. But all of these different defenses cause different scenarios in which you can design your robot, and it opens up countless different design opportunities. And our goal is to design a robot that can conquer as many of these as possible. And to talk more about that, I'm going to pass it over to Ian.
So part of our kickoff day is we're working very closely with Konawaina. So we're building defenses and they're building towers. We give them copies of their defenses, they give us a tower, and it's a good way to work with FIRST robotics teams in our community, and it's also a good way to prepare our field so that when our robot is up and running, we can field test.
Okay, so obviously the game strategy is really based around the idea that we want to score as many points as possible. So Sarah discussed the point system, so I'm going to skip this. But going over the design priorities is to get as many points as possible. So a lot of the points come from crossing the defenses. So if we look back at the defenses, they're really very similar. Category B and D are very similar, and category A and C are similar. So what we decided with that was to use the same kind of equipment that will cross both B and D as A and C. So the easy one is B and D. So to cross B and D, we just needed a really good drivetrain that would be able to cross relatively high obstacles. The rock wall, I believe, is about 6 inches by 4 inches wide. So it's really easy to get stuck if you have really small wheels. So we didn't really talk about it too much yet, but we got a base kit of parts, and some of it is still there, present on our robot, but we did some other modifications to make it able to cross the B and D obstacles. So the main idea was to cross the B and D obstacles, sorry about that, and just having large wheels. That was one of our design ideas, just to have large wheels that would be able to just drive simply over the obstacles. Other teams, one of their strategies, which we didn't quite agree with, was to use smaller wheels and ramp up and drive very quickly over the obstacles. Obviously, that's a lot of stress for the robot, so we went with larger wheels that would be able to drive over it easily. Another consideration was the fact that the low bar is always in the gameplay. So knowing that, if we can have a robot that is below what we figured would be 13 inches, because the low bar is 16 inches and the low bar is next to a ramp, it actually detracts from our actual available robot height. If it is just 16 inches, because of the ramp, it'll still actually hit the low bar. So what we determined was that we had to have a robot under 13 inches, which is what you can see what we have so far. And we're trying to build to keep under that parameter in order so that we can always cross the low bar. The next thing was our shooting mechanism. So there's a lot of options for a shooting mechanism. Some people use a wheel system that just has 2 spinning wheels that spin very fast, in which the ball will then shoot through, and you can shoot high or low goals. Other teams have a pneumatic plunger that simply whacks the ball really hard and will then shoot into the goal. So what we've been going off of is using a 2-wheel or single-wheel system, and the reason largely for that is it's very compact, and it'll give us the option of shooting high or low. It also relies a lot less on the compression of the foam ball. So what we figured, if we had a pneumatic plunger, it would heavily rely on how new the ball is. Over time, the ball gets a lot softer and it's a lot easier to compress. So we figured a wheel system would be a lot more efficient and consistent. So the other thing was obviously the category A and C obstacles. So looking at these, we're trying to obviously cross as many obstacles as possible in order to acquire as many points. So one of our ideas is to use a simple hinging arm that will be able to go over the drawbridge, pull it down, and let us drive over it, which would also work for the sally port, which is similar to a regular gate. Both of them are weighted so that they flip back into place if there's no pressure holding them down. Same thing with the portcullis. If we have some kind of rotating arm that can lift it up and then have it just simply slide over our robot, it'll be a lot easier to cross. And similar to the chevere de frise, if we either have a moving intake that will push down on, if you can see it, these 2 of the ramparts, we'll be able to then drive over it again, and it'll just be able to flip. Oh yeah, sorry. And one of the things that we really would like to do is be able to climb every time, but one of the big problems with that is that we want to be able to go under the low bar too. So a climbing mechanism has the potential to be very large, and that's not a great thing if we want to go under the low bar every time. So one of the things we're considering is to have a climbing mechanism that would be able to put on and off the robot that would be over 13 inches, so we wouldn't be able to go under the low bar, but we'd be able to climb. And because we're in an alliance, we don't necessarily need to be the ones going under the low bar every time. We can have one of the other robots in our alliance going underneath the low bar, and we could climb instead. And that could give us the maximum number of points.
So to clarify, to breach, you have to cross 4 out of 5 of the defenses, and then you get a rank point. For every match you win, you get 2 rank points. So breaching the defenses is like winning half of a match. So that's why we are prioritizing breaking through the defenses as much as we are. And next I'm going to pass it off to Emily, and she's going to talk to you a little bit about our kit of part spot and how we have changed it and optimized it. Here you go.
Okay, so I'm Emily. I'm a sophomore at Kealakhe High School, and this is my 2nd year as a robotics student, but it's my 1st year in the Kealakhe High School. So, going back to what Ian was talking about, mainly about our base. So we started on kickoff day. We kind of discussed it, and we're like, okay, so all these hard obstacles that we need to pass, like, it makes no sense to kind of use like all of our time getting a base together and building it ourselves when we could just use the parts that are already given to us and then just modify it from there. So that's what we ended up doing. So our base right now, or the base that they gave us first of all, was just was this metal base, and it had originally 6-inch normal wheels on it, but we ended up, the modifications that we made for that, so we ended up switching out the 6-inch wheels for 8-inch wheels just because it's easier to get over the obstacles such as the rough terrain and the rock wall, just because of how high they are. The 8-inch wheels are a lot better to use. Other than that, the other alterations that we're going to make are definitely that we move the wheels closer together because we didn't want to get stuck on any of the obstacles because of how far apart our wheels are spaced. Other than that, we also ended up cutting down our base, and we're going to cut it down some more, basically just so our bot fits within the size restrictions more and we can add more to it, as well as take off extra weight. And I think that's pretty much it.
Next we're going to have Skylar, and he's going to talk to you a little bit about the control systems and the importance of sensors in this year's game.
So I'm a member of this year's control system team, and this year and the year before we've had a big change in how we do control systems from switching from C++ to LabVIEW. We did this mostly in correlation with another project inside the team, and with the experience learned last year, being able to get carried over to this year and make programming a lot smoother. One of the big highlights this year is the NVIDIA Jetson AK1. What that's going to let us do is to scale the castle wall, they have reflective tape on each side of the bar. We need to be able to take pictures of the tape, scan it, and that's what the Jetson AK1 is going to let us do. It's going to be using gyros and encoders to be able to process the images faster and easier and take it off of the robo-reel.
Okay, so basically the Jetson is onboard imaging processing, and we're using this because a lot of this year's game is about imaging. In addition, we have the encoders, which we can use during the autonomous period to measure how far the robot is going, and the gyro to measure turning, so rotation of the robot. And so we're hoping with the use of more sensors and the simple interface of LabVIEW that we'll be able to use a lot more of our control systems and sensor capabilities to succeed in this game.
I'm going to pass it off to Lex.
Hi, I'm Alexis. I'm a freshman, and this is my first year. And this is our Gantt chart. So what it does is it organizes the different tasks we need to get done, and there's different due dates, so we use our time wisely, and there's different percentages on how complete that task is. So this is really good in tracking how much time we're putting into the robot and different places we're putting time into the robot.
So one of the great things about FIRST is it gives our students engineering experience, and what we wanted to do is we wanted to give them the organization of an actual engineering project. That's why we built this Gantt chart, and we have a student that updates it every week and changes it to what we're actually doing with the robot and updates the percentage completion. This year we're hoping to keep a lot more on track with the hours we spend and the rate of completion we have for each task, and Alexis can talk to you more about that. Next slide.
So this is our FRC work tracking form. So each member of our team fills out this form after they complete a task or complete a certain amount of time. They put in how much time they put into the robot. They put their name, of course, because we're not going to know who they are. They don't. And we can find out how much hours altogether from everyone working on the robot, and different tasks for FRC is put into the robot.
Alright, so the robot and tracking our work and facing not real engineering problems, but fake engineering problems that give us some real engineering experience is one of the things we really like about FIRST. But another thing we really like about FIRST is our outreach opportunities, and Isaac and Lily are here to talk to you about those.
Hi, I'm Lily, this is Isaac, and we are both juniors, and we just started in the robotics program this year, and it has been an amazing experience. So what we will be touching on is our outreach, and I think our outreach is one of the things that we like to pride ourselves on because we really like to give back to the community, and that's also touching on values. That's something that we like about FIRST. They share some of the same values that we have, which is really amazing, and they present an environment that we can thrive under. So one of the events we put on is FLL, and that is FIRST LEGO League, and it's for 1st through 8th graders. And at this event, they presented their environmental issue, and they presented in a way that they could sort of a solution for that environmental issue, and they also got to show their bots, which is really amazing because it is like, for some of these teams, it's the only time in the entire year that they get to show their bots, which is awesome.
What's really awesome is that not only does the community get to come together and learn about STEM opportunities and things that affect these kids, and they have learning opportunities for science, technology, engineering, and mathematics and stuff, but it's that where a lot of the other teams come together and they can see each other and feel more comfortable around them. And also, it's where the community, we want to inspire the community to be a part of more of these types of events and activities. And when the community dedicates their time to show that they really do care about our kids and students, even the little ones doing their first Lego League, it really inspires the kids, and it makes them work harder and really look at how to achieve their goals and things to do in life. And teamwork is a very important thing to us, especially our robotics team. Cooperating with each other and definitely making sure that everyone is treated equally and being able to share their views and opinions on everything. Yeah, so pretty much that's it.
What was awesome with the FLL tournament was that we planned on having a bunch of booths come, but we actually put it on all by ourselves, which was, we thought it was a detriment, but it was actually sort of a blessing because it showed us that we could really put on an amazing event that was really fun for kids all by ourselves. Like, we had a photo booth, and we had a bunch of different mini games, and we had a tiny town, and we had some other cool stuff like face painting. And not only, it showed the kids that that learning can actually be like so fun, and that this stuff really pays off, which is something that we've tried to tell them, is that if you pursue STEM, it will really pay off in your life. We also put on a scrimmage before that where we dressed up in Halloween costumes, again, just trying to show them that STEM education is fun. And this just allowed them to present their FLL stuff before that so that they could improve from our suggestions. And yeah, it was really fun for all of us, I think, just to interact with the kids. And it was nice just to know that we could really make an impact on the community. Okay, I'm just going to hand this off. Room time.
So these are, that was about 15 of our kids. So our program, we're now in our 6th year. And this project is one of 26 different types of projects that they'll take on. So we'll travel with 65 students to about 30 competitions this year, 5 trips to the mainland, about 20 inter-island trips, to give them exposure to what it looks like to be a high-performing professional in a variety of STEM fields. So, you know, when we look at this project, it's one of the bigger ones. It has $20 million in scholarships dedicated just to it. And our students have leveraged the program to a lot of opportunities at great universities. But again, it's just one aspect of it. And so we like to come to the community. We'll be doing about 40 to 50 community events similar to this, kind of telling our story and letting the kids, so this is my first time kind of seeing their presentation. I think they did okay, right? Letting them kind of talk about their learning process and what it means to them to develop into young professionals that can eventually lead to a more resilient and sustainable community. So we'll be here for a while. We have some of the engineering of a robot, some cool, I've been in a lobby for a while, so I'm kind of seeing this for the first time. Interesting wiring decisions, we'll talk about that. A lot of things to talk about later, but I'm going to go ahead and bring up some of our student leaders. Actually, I'm going to just randomly bring up some kids, because we're going to take some questions, and it's really great for you guys and gals to ask them some hard pressing questions, because we want to prepare them to be able to kind of think on the spot and explain the project in a way that's both accessible, accurate, and also technical. And of course, a big thanks to Rod for putting on these events and Alha for hosting, and a quick plug for the wonderful partners that we need. So just as a fun aside, the program is not school funded. We're independently funded, and it has about as much like revenue cost as like a Taco Bell, right? And so, think about Taco Bell, they have a lot of stuff coming in and out. And so we have wonderful partners like Nelha that help us put on things like the science fair and like AIA, which really partners with us in pretty much all of our outreach events. Really appreciate that, Sean. And so all of you have networks that can like help partner. And the biggest partnership, we're okay on money. Well, money's great, but the biggest thing is like there are professionals and industry leaders, many of whom are in the room, and the kids should be interacting with them more. And so you should come by and hang out with us. We have cool facilities and fun toys to play with. So now, to further encourage you to do that, you can ask them like hard pressing questions. I'm going to bring up people. I'm going to bring up, sit down, Courtney, you've talked a lot. Blake, who's not in a team shirt, he's a senior. You can come up, Blake. And Ian, it's your first year, so you can get up here representing the juniors. Sophomores. Yeah, Emily, are you the only sophomore with us right now? Okay, well, come on up, you. Lisa, you're not going to say anything when I bring you up, right? You're just going to stand there. I'll take Alexis. Okay, Alexis, you can represent the freshmen. And so, yeah, stump them and challenge them. And also, we're going to space, which we didn't even talk. Did you even tell them we're going to space?
This is FIRST.
This is FIRST Robotics. Yes, this is FIRST Robotics, but the program has a lot of other things. Yeah, don't talk about that. But talk about anything you want now. There's questions. Yes, Paula.
So a question for Blake. Since you're a senior, toss you in first. Comment, if you will, on the things that you learned that you think will carry forward as you move into your next phase of life, which is hopefully college. And how's this program helping you?
It's kind of a lot of things. I've learned to think on a more professional level, which I think is the most important. I look at a problem, and I don't look for what is always the first solution. I try and think it through several different ways, because the first time you look at something, it's usually not the correct way.
Where did you apply to college?
Georgetown, Columbia, Michigan.
Okay. What are you going to major in?
I'm thinking foreign relations.
Yes, for anyone who wants to take it. What is your team decision-making dynamic? You talked about design goals and objectives and this sort of thing. How do you as a group decide what you're going to do?
I task it to a student.
That's how I described it. So robotics, obviously, because we encompass such a broad number of programs, we really have a lot of different subgroups that kind of do different things. So if you notice, like Isaac and Lily, they do a lot of our graphics and stuff. So like this presentation they made, or some of the presentations they helped make, and a lot of our pamphlets and words they do. So we actually kind of have a sub-design team. Me and a couple other people are really heavily involved. And we just kind of discuss a lot on the first day. Everybody kind of learns the rules, but usually there's about maybe 6 to 10 people who have a really big influence on the design of it in general.
So each week we'll have design group meetings, which kind of update on the process, and then we can kind of say like, if you look back at the Gantt chart, what are some critical decision points, right? So one of the things we decided this year is we need to decide on our base early on, because it's going to influence so much of the later on design. So we're about a week ahead of where we typically are as far as base design, because we knew that as we got into the obstacles, making that base solid was going to be extra important. And then from there, there's integration. I think this is the first iteration. I don't know how much you guys did yesterday, actually. First iteration of a pickup design. This week we'll probably be finalizing the pickup, right, and then starting to move into the shooter. So you can kind of look at the project and then see which ones of those are interdependent. So can't really shoot if you can't drive and collect balls. So that's going to be that third stage. And each week the students will kind of meet and talk that out and lead to CAD decisions, which lead to building decisions, and then the building things that match up with the CAD, and like look at that, cry a little bit, and stay late and fix it.
That has not happened yet.
Not yet.
Get that clear.
You're going to answer the next question anyways. Been on the team for 2 weeks, we'll see how she does.
Sid.
Yeah. If 8-inch wheels are better than 6-inch wheels, why not go with 14-inch wheels?
Well, that's mainly because I don't even think they make wheels that big, first of all.
Definitely do. 100%. Tires exist on cars.
I'm pretty sure they have like size restrictions for FIRST for wheels, but it's mainly because our big decision that we made was that we want to be able to go under the low bar, which is like what, 14 inches. So we have to be under 14 inches.
12, sorry, 12. One of the big things with the tires is that they're pneumatic wheels, meaning they're similar to our car tires, they're just inflated. So one of the big things with this is that because we're kind of driving over them very roughly, we figure that extra cushion will really help and not make it quite so rough when we're driving over everything. The previous wheels are just kind of have a rubber rim, not much else.
So that probably gives a good reason why we had pneumatics as opposed to solid rubber wheels. But I still want to push all of you on the idea of why 8 versus 10 or 12.
Because we gotta get under the low bar. You can't get under the low bar if you have 10-inch wheels and then the robot is sitting that high.
Because of where your axle is.
It's just because it's always a constant on the field compared to every other obstacle. So if you can get under that one obstacle, and let's say like an arm of yours breaks, so you can't like go under anything else, but you know you can get under that low bar, so you can still score points no matter what, as long as you can get under that low bar.
And partly because we're obviously trying to have a design parameters of 54 inches long, and we want to kind of stay more compact. Obviously these are 8-inch wheels, just another inch on both sides would have them almost touching, which we want a little more width on that.
How about 4 wheels instead of 6?
Because we want small gaps in between them. If you notice with the rock wall, but the big thing is some teams are getting stuck in this little gap if their gap is too wide between 2 wheels. So right now, if we had the rock wall, it would still be touching both wheels and let us drive over it.
That's not better answer.
You just mentioned some of the other teams you're seeing people getting stuck. Does that mean that you and the other teams are all sharing information?
So one of the cool kind of like adult competitions they have is they have what's called Robot in 3 days, and they watch the first release videos and all of that, and then they have to make a fully functional and working robot in 3 days. So what's great about that is it just gives you a lot of kind of general insights in what you can do. So some of the basic concepts, we actually looked and like helped learn from them. Like we noticed that the teams with the smaller wheels got stuck on the rock wall, or that the teams with the smaller wheels had to launch themselves up the ramp in order to get over the rock wall.
So the Robot in 3 days is all professional engineering teams. And you kind of learn from them. And a big part of the community is that you post. So every single week we make a video kind of saying everything we're doing, right? So there's kind of, well, some teams will take a secretive approach, but we as well as most of the community take an approach of as we're learning problems or as we're learning about things, then we're going to post it online for everyone to see. And then we're constantly looking at what other people are doing online to see if we can save ourselves some time and see some unique insights from their resources and time that they put into the problem.
Did I see on your Gantt chart that your timeline ends in mid-February?
I believe you did see that.
That's like 3 weeks from now.
You're right.
Wow.
It's a 6-week project, so this is the beginning of the halfway point. One of the biggest problems that sometimes the kids don't know about is when you look at supply chains coming out to Hawaii, none of the type of specialized parts we need are here. And so we just had a big, like, 10-day shipping delay, which when you have 42 days, 10 days is a lot, particularly for something that's foundational. And so as much as we want to organize in our Gantt chart, we always got to switch those things around based on the shipping days, sometimes based like the kids have other things going on in their lives, disastrous, right? Right?
What?
So
School?
There's some flexibility there, but it's a hard deadline, and this thing goes in a box, and we're going to Florida as our first competition, so it goes in a box and gets shipped away right away.
Wow.
We got to build that box in those 6 weeks too. Who's building the box? We have a box on the chart.
No.
Oh.
Alright.
The chart, please, like this.
Have you tested this base yet?
So actually that was our big delay, was the actual wheels for the foundation. So we just got the wheels on like fully Friday actually. So, and we have not tested,
I don't know.
Yeah, we actually have not tested into fully driving and stuff yet. We basically, for the testing the rock wall, we hold half of the side and we kind of shove it over and see if we get stuck. And just yesterday yesterday we had a big build day, and we just start off, we build a lot of things out of wood. So by tomorrow we should be driving because all of our motors are connected. We just need to get our electronics all hooked up, and I believe our programming is all good too.
So we were able to get a driving robot 10 days ago, and then took some things apart based on what we learned from that, and we'll get this one. So, and that's the fun thing, and this is why you guys should all come by and check us out. We're there all the time. Just go to the school. We're the only ones that are there. Tomorrow, this thing, it'll look very different. Very, very different, and every day it'll morph. And then at the end, we'll take it all apart because we want to powder coat it because pretty's good, right? And then we'll put it all back together. And when we put it all back together, the great thing is then we know how to build it. We know that we have the tools exactly that went into it. So like 3 days before the competition, we're going to be a big barrel of parts, powder coat it, and then put it together and ship it off.
What's the size and weight of your boulders?
So they're 10 inches in diameter and pretty light. They're just a dense foam ball.
Like a basketball, sort of.
Yeah, so like a basketball. Okay. We can imagine a foam basketball.
And it's foam? It compresses?
Yeah.
Rod?
Yeah. So one of the things you haven't talked about yet is the various manipulators that you might use to breach defenses, throw things up. What are some of the ideas that you're tossing around?
I don't know. I can operate the computer.
So I think we have it on our CAD design, but currently, like I was going over with the defenses, we have 2 things in mind.
F5 does something different on Courtney's computer than it does on mine.
I think that was their test music for testing the sound. Yeah, in there. See what we have in there. Yeah, okay. So one of the just general concepts is that right here, I don't know if you can see it, but we plan on having 2 Lexon sheets just on the side, and that's for the portcullis, and everything so it can just slide over. This part is one of our options for lifting the portcullis. It's just 2 simple bars powered by a wheel that would be in the front. That would just lift the portcullis up slightly and then flip it over. We're not totally sure about on the front or back yet, but we also plan on having some kind of 2-joint arm that, if you imagine like a 2-joint, that's really weird, a 2-joint arm that can lift over and grab onto the drawbridge and grab onto the sally port and then pull it back. We can then drive up over it, or in the case of the sally port, which is kind of like a gate, we turn off to the side and then kind of shuffle our way through it while holding the door open. So those are our 2 main plans.
What about our hanging mechanism? I wonder who's in charge of that.
I don't know. So our hanging mechanism, right now we're kind of holding off on it because it just depends so much on how we design the robot otherwise. So I'm kind of in charge of the hanging mechanism, and I think I'll have like the last week or so to figure all that out. And so one of the things is that there have been competitions in the past where you have to lift your robot off the ground, but in those cases you only had to lift it up a couple inches. In this case, we're lifting up a couple feet off the ground, and we have to stay above a fixated line. So we have a lot of options going around there, from a kind of an elevator system that would have several bars that would be lifted up by a system of pulleys, and then lift up and then pull it back down, versus even if you imagine a measuring tape, how it can shoot up and then extend back down. We don't necessarily need a push up, all we need is something to pull. So if we can get that measuring tape up to the top, hook onto it, and then retract it back down, that'd be another way of getting out.
Do you have any rules to say there's things you can't do, like paintball or explosives?
I don't think that's a good rule.
This scared me napalm. Incendiary device.
There's definitely some unsaid rules.
No, I'm pretty sure that one's covered by the existing rules.
Explicit rules excluding napalm and such, but there are rules that you can, I think, poke inside of other robots.
You know that. Does it say if you got something in writing?
The rules are very comprehensive.
And then
there is stuff in there about flames and actually specifically attempting to damage another robot.
Something general that would cover all of that.
This isn't combat robotics.
You gotta know Sid. Don't worry. So, as you guys, I thought you said you could make contact with another robot, or other, how, does that bring an offense and defense to your plan and strategy, or what are you gonna do if somebody's bashing up against you?
For sure. So that's why they have rules about a certain number of robots inside your defensive zone at a time. So back in the beginning, you can only have one robot in your area, so that kind of inhibits defending. Another thing to note is that all the robots have actually a bumper extended out around surrounding it, so that protects the general frame of it.
All right. So in your design right here, that bumper's going to protect the wheels as well, as like a.
So if you imagine
just
like
straight out?
even like a 2x4, like all the way circulating around.
So another robot could come up to this robot here and drop a little metal ball right in front of your wheel there, right?
I don't think so. I think that goes within the series. And there's another rule that I think, I don't know what the design parameters are, Courtney might know it, but that you can't extend past a certain distance.
You can extend 15 inches on the side of your frame. And then, so you can't pin. So you can hit 5 seconds, you have to drive away, and if it looks like you're following them, then you can get penalized for that. So
you can't at any point intentionally go inside of their frame perimeter, but you can hit them as hard as you want. And so when we built kind of a super drive base a couple of years ago. Myself, Mr. Houck, who's about my size, pushed against the wall as hard as we could, and the robot could topple us over. So we had 900 pounds of force, and we moved at about 15 miles per hour. So you can imagine, if that hits you, it's pretty gnarly. And robots crack and break, and welds crack in competition. Whatever happens in competition, you got to fix it in competition. So at internationals, NASA brings out their mobile machine lab to help you with that. Locally, BAE Systems sponsors a similar lab. But everything has to have failure points tested and backups, because it's some pretty gnarly hits. And while they're not supposed to go in, if they topple over on top of you, which happens a lot, then you got to make sure that you're okay with that. So we will have a full Lexon shield, and everything will be encased completely, 100%. For me, access to.
How are, in competitions, how are alliances formed? Randomly.
But the highest ranking teams, whenever they hit finals, going to pick alliance members.
So every team has a set number of matches in the qualifying rounds, and then you are randomly matched with your alliance, and then you are with a different alliance every single time. And then for finals, the top 8, they pick, and you form alliances, move backups, and then you go from there. So that's why the rank points are important. You can go up in rank, and rank points get you to alliance match picking.
No, it's fine. So the higher your rank, the more likely you are to be able to choose in the final.
You want to be able to choose. You want to be ranked high to choose, but then you want to be ranked low enough so that like good teams choose you. So it's a lot of theory. We have scouting teams for that, and we're getting some tablets so we can scout which defenses people can cross and what rank do we want to be when we're picking. Like quite strategy.
Alexis gets to answer whatever you ask.
I was curious about your controller. Like, what controller do you use, and what operating system does it run? And is the application that you're running is it custom developed, or is it something you've gotten from somewhere out on the internet, or what? Just could you comment about that a little bit?
Can you comment about that a little bit?
So the controller that we use, it kind of looks like, have you ever went to an arcade and there's like this one stick and then you kind of wobble it back and forth to control like your character or your car? So it kind of looks like that. It's a joystick.
Yeah, well,
I was talking about.
I was thinking about the computer, the boards.
That's actually determined by FIRST. They assign a specific controller, and you must use it.
Oh, okay.
It's a National Instruments.
Okay.
That's not correct. We use LabVIEW to program all of our robots and all of our controls, but I have seen and I have been on teams in the past where instead of using the given joysticks, you can use Xbox controllers as well, or just any type of controller that you're able to program within the restrictions of FIRST.
Okay.
So I know some people, they find it easier to use the joysticks, but other people, they find it easier to use Xbox controllers because that's what they're used to. So it's more just driver preference.
Yeah. Okay.
wanted. It's onboard imaging. That's what they've been doing with their time. And so now we're learning to interface that with the cameras. We had some camera system issues in the past, but we fixed those so we can run imaging through LabVIEW, but for faster, more efficient imaging, and so that our sensors come in on time and accurately, we're going for onboard imaging, and so we're switching to Ubuntu and we're switching to Jetson. So.
Then, might be down in the weeds, but are you using OpenCV for your image processing? Or?
I am not sure.
Yeah, so we're gonna have to do there's some stuff on that, but we're gonna have to do a custom interface development for to get it back to what we can do, which is regulated by FIRST, right? So we have to take that and then take it back there, and that's not a standardized package yet. So we'll have to develop that in the next 4 weeks.
Okay, there is an OpenCV LabVIEw then.
Can you explain why is the imaging so important for this game?
So,
Data strategy.
so when shooting, there's that reflective tape right there. We're looking for an accurate shot. There are changes in the ball compression and the speed of the wheels, and we need to be able to make that shot hopefully every time. And so definitely during the autonomous period and even during polyop, onboard image processing is very important for in the moment configuring and shooting. And so that's why we're making it such a priority this year with control systems.
Are we going to see some video footage of how well you did?
Yes. Absolutely. Next year.
The competitions are live on the internet if you want to watch them when they happen.
Okay. So Blue Alliance is a great website that has all the competitions and all the matches. We're 3880. All the teams, so we have 3,880 team to join. They're at about 6,000 now. So all the teams are online. You can check them out. We'll be at the Orlando Regional, which is a week 3 event, and the Hawaii Regional, which is a week 5 event, and the championship event once we qualify, because we're going to qualify, and all the matches are online. So you can see them. They're pretty cool to see, 650-pound machines built by students smashing into each other, scoring balls, and then by the finals, these things are zipping. So check them out.
How does your robot autonomously recognize those color stripes and convert it into what it does to take action?
So we have a series of sensors and interfaces. So the nice thing about LabVIEW is they come in packages. So before when we were using C++, it was a lot more difficult to pull the code and write for that. And with LabVIEW, we're having fewer errors. But we have line sensors, light sensors, sonic, ultra rangefinders. We have just about everything when it comes to distance, imaging, and seeing differences in light and reflective tape.
So it's take those 3 different looking towers.
Oh!
Your thing knows which one is which.
One tower on each side.
Okay.
Just one scoring tower. So this just right here, when you score balls, it weakens the tower. And so once you weaken the tower, you can capture the tower. And so this shows the progression of scoring. But if you see the gray stripes around the shooting, or the scoring right there, yes. You see those? That is what the robot is onto.
Yeah, this isn't the reflective tape. These are LED panels just letting us know if we've killed them or not, right? Super exciting for the kids to learn that lesson. And then right here, this is what actually gives them the imaging.
But how does your robot take some physical thing, like a tower, look at it, translate what it sees into some information that somehow directs the robot to do something?
So it comes in like difference in numbers. So we have the sensor, and then we're seeing what value we're getting for shining the sensor onto the reflective tape, and what value we're getting when we're not shining that tape. And then we can write code based on those numbers. and that's what I did when I was using C++. But with LabVIEW, over the years, they're just making it more compact and compact. I don't even have to write a code for the compressor anymore. I just have to say, I have this solenoid, and it compresses automatically. So this year, a lot of the imaging and a lot of the sensors are pre-built by LabVIEW.
So there's something in your program that knows what that's supposed to look like?
Yes. Yes, I can set values.
So with that, I know you want to get back to the networking time, but every Tuesday and Friday and pretty much every other day forever, we're at Kealakhe High School. We'd love for you guys to drop by. Our kids are in blue shirts, and also some are not. But please network with them and talk to them and amongst yourself. And a big hand to Rod for putting this on. Really appreciate it.